Professor Nelson. My name is Avi Dayani, and this is my submission for the final project for Calculus 2. The first topic that I'll be discussing today is the fundamental theorem of calculus. Before I begin, I'd just like to explain that I've broken out my explanation into multiple steps, steps 1 through 10. This allows me to reference different steps as I move along. So just wanted to make that clear before I begin. So let's dive straight into step 1. In class, we define the definite integral as the limit of Riemann sums given a partition of a comma b, which is what I've written out in step 1 right there. On each interval of xk minus 1 comma xk, we pick a sample point ck, and then we can draw a rectangle of height f of ck with the width of delta xk. The Riemann sum is the total area of those rectangles, as I've written out in step 2. Um, we can then see that as we refine the partition more and more, that's to say that rectangles become thinner, these sums can settle down to a single number. And if all choices of sample points give the same limit, we can say that f is integrable on a comma b and define the definite integrable, which is what I've gone ahead and done in step 3 right there. Um, what this basically tells us is that the integral is the true area under the curve from a to b. Then moving on to step 4, we can see that instead of computing that limit every time because it's so tedious, we can pivot to using the fundamental theorem of calculus, which brings us to the area so far function, which I've written out in step 4. Um, this tells us that for each x between a and b, the antiderivative is the area under f, the function from a to up to x. Now imagine moving that x a tiny bit to the right from x to x plus h, which is what I have sketched out here under step 4 on the left. Um, this change in area is the antiderivative of x plus h minus the antiderivative of x, which is roughly the area of this thin rectangle, which I have colored over there. When we take this limit, when we take the limit of h tends to 0, this approximation becomes even more exact, as we can see in steps 5 and 6 over here. More specifically, step 6, we can see the effect the limit has. This also matches our textbook notes, as this is theorem 17 from the notes. In this particular model, we can see that in this particular model in step 7, we can see that the total area under the function from a to b is the area so far at b minus the area so far at a. This now let's use the fundamental theorem of calculus that we've just learned to solve an original example, which I've written in step 8. The example is right here. 1 plus x is the function that we're going to be working with. Instead of going back to Riemann sums and rectangles, because that's really messy, we're going to use the fundamental theorem of calculus to first find an antiderivative and then plug in the endpoints, which is what I have done here in step 9 and also 10. This f satisfies the fundamental theorem, so I've gone ahead and just plugged in the values. This tells us that the exact area under the graph is under the graph of 1 plus x from 0 to 2 equals to 4. This should demonstrate clearly the power of the fundamental theorem as it turns turns the limits of Riemann sums into a simple antiderivative calculation. My second topic is infimum, supremum, limit infimum, and limit supremum. So let's begin with jumping right into step 1. First, I'm going to talk about bounds for sets of real numbers. If I have a set X of real numbers, a lower bound is any real number that sits below every element of the set, and an upper bound sits above every element. So if the set has both an upper and lower bound, we call it bounded as written. Then among all upper bounds, the best one is the supremum, which is denoted by sup x, which is the smallest number that is an upper bound. Similarly, inf x is the greatest number that is a lower bound. So sup and inf are tight bounds, which means that you can't move them inwards without them failing to be a bound. They are not necessarily a part of the set, but they potentially can be. Let's further clarify this using this example over here in part 3. As we can see, each term is less than one, but it gets closer and closer to one as n increases. So in the case of the infimum, we know that the smallest element we see is when n equals to one, because the output is zero. Every other term is bigger than zero, hence zero is the lower bound. And since it is also in the set, it is also the minimum. For the supremum, we notice that all elements satisfy the 1 minus 1 over n is lesser than 1. So one is the upper bound, and to see that it is the smallest upper bound. Suppose there was some smaller upper bound, we can denote this as m great, like capital M is lesser than one. Then the gap of one minus m would become positive because the terms one minus one over n get arbitrarily close to one from below. We can choose an n large enough that one minus one divided by n lesser than m. This contradicts that m is an upper bound to begin with. So no number smaller than one can be an upper bound, and sup x then equals to one. So this set has an infimum, which is also the minimum, zero, and the supremum is one, but it never actually is in the set, so it is not the maximum. Now let's move on to sequences. Given a sequence of an. The n tail is just the sequence starting at like tiny n equal to capital N. So everything from a subscript capital N onwards, as I've written over here. So a capital N comma a capital N plus one, etc., etc. So in this scenario, Sn is the supremum of the n tail, and In is the infimum of this n tail. So the limit inferior and the limit superior, as per these definitions, are the limit inferior is the greatest number that is below almost all terms of the sequence, and the limit superior is the smallest number that is above all terms of the sequence. Um, this goes ahead and proves an important theorem from class, which is lim inf of an must equal to lim sup of an for there to be a convergence. Uh, Now let's use what we've learned so far to solve our own example, which is over here in point seven. The example sequence is an equals to minus 1 raised to the power n plus 1 over n. I've written out the values for a1, a2, a3, and a4. So if we are to look at the tails, I've also written this out. If we are to look at the tails, the largest values come from the even indices, um, whereas the smallest values come from the odd indices, and the greatest lower bound equals to minus one, whereas the greatest upper bound equals to one. We can deduce from this that the limit superior and the limit inferior are in fact different. Hence, the series does not converge to any single limit. For my third topic, I'll be discussing the Taylor series. So let's jump right into it with point one. A power series centered at C is the infinite sum of the form that I've written out in step one. Each partial sum is just a polynomial, so you can think of a power series as somewhat of an infinite degree polynomial. For each fixed x, this becomes an ordinary series of numbers that can potentially converge or diverge. The set of x values where it converges is the domain of the function defined by the power series. So this leads us into point two, which is related to deciding the coefficients ak so that the power series actually equals f of x. Um, Now, suppose we have this function that I've written right here. When we plug in x equals to 0, every term with x vanishes except the first. So f of 0 equals to a0, and then so on and so forth. We keep repeating this idea until we eventually land on this general notion that the kth derivative at 0 always satisfies this rule that I have written out over here, k factorial multiplied by the coefficient. So that then goes ahead and gives us the value for the coefficient, which I've written out over here. That this is to say that the coefficients are completely determined by the derivatives of f at the center. Now let's jump to point three, which exposes us to the general Taylor series formula. This does the exact same computation, except instead of x, it does it with x minus c. If all derivatives of of f exist at point C, then the Taylor series of f centered at C is what I have written out in part three. When the center equals to zero, then this is known as the Maclaurin series of f. Um, we can also further evaluate this using this original example for the Taylor series for cos x at c equals to zero. So using this formula to find a concrete series, we can compute the derivatives of cos x, which I've gone ahead and listed down over here in part four. Now when we plug in the x equals to zero into these derivatives, um, we can then get the Taylor series formula, which I also have over here, 1 minus x squared divided by 2 factorial plus et cetera, et cetera, et cetera. Um, Now the notes define the nth Taylor polynomial. So you just stop the infinite series after the x raised to the power n term. For cos x at zero, I've written out what it would look like. Similarly, I've done the same for for the degree two Taylor polynomial, and then also the degree four Taylor polynomial. The textbook describes these as tangent polynomials.